Hey everyone, so I want to talk a little bit about electrostatic forces and the electric fields. Now, you should have already completed the worksheet that actually goes over most of the electrostatic forces. Honestly, it's pretty much copy and paste from the gravitational forces. The equation looks almost identical. The same tricks that they do with the gravitational force applies with the electrostatic force, with the whole scientific notation. Graphs are identical. The whole idea of the 111 method also comes up. Honestly, the only difference between the electrostatic force and the gravitational force is that sometimes it's attractive and sometimes it's repulsive. That's it. Um, in fact, most of what I'm going to actually focus on in this video is really about the electric field, and even that is should be fairly quick. It's going to be mainly concepts. So the electric field is basically the area of effect where if you're inside it, there's you're going to be affected by the electrostatic force. That's pretty much what's going on. Now, this is actually very similar to something else called the gravitational field. So massive objects, or any object that has mass, has a gravitational field around it where, again, if you're inside it, you will feel the gravitational force. So, if we want to know what the gravitational field around the Earth looks like, it will look like this. The way we actually figure it out is that we just ask ourselves, what direction is the gravitational force? If I put an object here, where my cursor is, what direction would it go? Well, it'll go towards the Earth because gravity always attracts objects towards it. If I put it above the Earth, it would go down to the Earth. If I put it below it, it would go up to the Earth. Over to the left, it goes to the right. So it's no matter where I put it, it will always go towards the Earth. So this is what the gravitational field will look like around the Earth. And I could do this for any mass object or anything like that. Um, Now, here's the big problem. With the electrostatic force, as I just mentioned a second ago, it can be attractive or repulsive. If I tried to do that same thing for, let's say, around a positive charge, well, depending on what type of objects I put next to it, it would either attract to it or repel. So, which one do I choose? Do I choose to look at what's going on with positive objects or what happens with negative objects? The way we do this is we ask ourselves WWPD, or what would a proton do? So every single thing about the electric field, we're going to be constantly asking ourselves, what would a proton do if I put it here? And that's what the electric field does. So the arrows that the electric field shows is always what a proton would do. All right, so here's our electric field, and now we have a proton, or a positive object. Now we're going to put a very, very small positive proton right here in this corner. If I put it here, I then ask myself, what would a proton do? Well, a proton would go away from it. So the proton would move away from the positive object. I put the proton here. Once again, what would a proton do? It would go away. Put it here, goes away. There, goes away. So no matter where I put it around this positive object, it will always go away. So the electric field around a positive object or a proton would look like this. Because wherever I put a tiny, tiny proton, it would always go away from it. All right? So that's what the electric field around a positive object looks. I could do the same thing around an electron. I put a positive proton over here. What would a proton do? Well, opposites attract, so it would go towards it. Put it here, towards. Put it over here, it will go towards, and here it would also go towards. Once again, no matter where I put it, it's now going to go towards the negative object. So the electric field will look like this. So notice it looks pretty much identical to the electric field around a proton or a positive object. The only difference is now the direction of the arrows. Instead of going away, now they go towards. There's other fields. So unlike with the gravitational fields, we don't really see too much of multiple mass objects. Here, though, we do get something a little interesting. So we can have the electric field around two positive objects, in which case what ends up happening is the arrows will still go away from them, but you end up having this like smushing effect in between, where there ends up not really being a electric field, mainly because it actually gets canceled out by the two positive objects. The other thing is, if this field actually looks identical to two negative objects, I don't think I have a good diagram of that, but the only difference is that the arrows go towards. So regardless of whether it's two positive, two negative, two like charges will always produce this like bending effect of the electric fields. And then the other one of note is a proton electron, or a positive negative. Here you end up getting, again, the electric, what would a proton do? It would go away from the positive object, but then as it goes away, it will start to get attracted to the negative object and will start going towards it. So again, what would a proton do? Away from the positive object towards the negative object. So, as I said, the field lines always answer the question, what would a proton do? Now, this is extremely important because one thing to remember is, do protons actually move? No. This is actually one of the things that can make this topic confusing, is that a lot of the typical phrasing, a lot of the conventions that we use in this class is always about protons and what they would do if they moved. But unfortunately, protons never move. So it's always the electrons. This is important because a lot of times what they'll say is the electric field goes in a certain direction, and then they want to know what happens to the electron. Well, the electric field always answers, what would a proton do? Negative electrons are the opposite. So if the field goes to the right, that means protons would go to the right. Because negative charged electrons are the opposite, they would go to the left. So it's important to kind of remember that, and that every time you see the phrase electric field, remember that that means, what would a proton do? A proton would go there, therefore electrons do the opposite. Some things to remember about the electric field lines, because this is actually, it's likely that not only will you have to recognize properly drawn electric fields, you should be able to actually draw properly drawn electric fields. Yeah. So one thing to know about the electric field lines, they always go out of positive and into negative. So you can see that anywhere there. The lines always go away from positive objects because protons are always repelled, and then they're attracted to negative, so the lines would go into the negative. Another important thing is that the field lines never cross. If you look at those drawings again, you'll see that the lines never actually cross each other, because that is the basically the net effect on the object. And then another thing to remember is field lines are closer, represent stronger electric fields. If you actually recall, these are the exact things that I mentioned about the gravitational field lines, and that's because they're the same thing. Like I said, the only difference is that one's dealing with electrostatic forces, the other one's dealing with gravitational forces. So here's a good question. Where on here is the field the strongest? So pause the video, work itself, we'll go over in a second. So once again, the closer the lines, the stronger the field. The area where the lines are the closest is B. Here's the next one. Pause the video, work itself, and we'll go over in a second. All right. So they want to know, where will the field be equal to 0? So where will they actually cross out? Now we have two choices. This is a typical multiple choice question, so there actually were other choices. But in these two choices, if I put the object at Y, it's being repelled to the right by both A and B. Remember, we're talking about what would a proton do. I put a proton here, it would be pushed to the right, caused by A and by B. But if I put a proton here, A is going to push it to B, but B is going to push it to A. So right directly in the middle, if A and B are the same charge, same value charge, they're going to exert the exact same force opposite each other. If you recall, the diagram that had the two positive charges looked like this, where the lines kind of mushed away, and there were no lines in the middle, and that's because in the middle they actually cross out. So X is where the field will end up equaling 0. All right, here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so here they want us to figure out the charge on A and B. Well, if we look at this, because of the fact that the lines are going away from one and towards the other, that means that it can't be C and it can't be D because they're in those cases they're both the same charge. But here we have the arrows doing two different things, so that means we have to have different charges. Since the lines are going away from A, well, what would a proton do? If a proton's going away from A, that means it's being repelled by A. And only like charges repel, so A has to be positive. And if A is positive, B is negative, which again makes sense because as it gets repelled from A, it starts getting attracted to B, and opposites attract, so B has to be negative. Now, there actually is an equation to figure out what the strength of the electric field is. The electric field strength is given is represented by the symbol E, and it's given by this equation: E equals Fe over Q. So E is our electric field strength, Q is the charge, and F is the electrostatic force it's experiencing. Now, the electric field is a vector. As we said, it always answers what would a proton do. And the unit is newtons per coulomb, which makes sense because the electrostatic force is measured in newtons, charge is measured in coulombs, so newtons per coulomb. It's a really easy equation. We'll do like 2 questions on it. So here's the first question. Pause the video, work itself. We'll go over in a second. All right. So if you look at this, they want to find the electric field. This is really the only equation so far that has the electric field. But unfortunately, they only tell us one number. Or do they? They mention the electron. The electron has a known charge. It's on the reference table. It's a charge of 1 elementary charge, which is 1.6 times 10 to the negative 19. You need to make sure that you remember this because anytime they casually say an electron or proton, you know not only the mass that's on the reference table, but the charge. Protons and electrons both have a charge of 1.6 times 10 to the negative 19. So plugging both those numbers in, we can find that the electric field strength would be 1 times 10 to the 11th newtons per coulomb. All right, here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so this one's a little bit easier because we have all the numbers. We once again use the electric field equation. We're looking for the force, so we plug the electric field that they give us and the charge, do our math, cross multiply, and we end up getting that the electrostatic force is 2.24 times 10 to the negative 3 newtons. And that's it. Like I said, it's about being able to recognize and draw the electric fields properly, remembering that the electric fields answer that very important question of what would a proton do, and then the equation, which, like I said, is very straightforward, very basic. Actually looks almost identical to the gravitational equation if you didn't recognize. But that's it. If you have any other questions, feel free to let me know. Message me on Remind. That's it. Good luck. Have a great day. I'll see you later.